Okay, so hello again. We now start with the contributed talks from the people who submitted abstracts to the workshop. The first one is Dominik Dold from ESA in Germany. And the topic of this talk is spike-based embeddings for multi-relational graph data. Stage is yours, Dominik. Thanks for contributing.
Thank you very much. So hello, everyone. As already said, my name is Dominik. First of all, I'd like to thank the organizers for organizing this really awesome workshop and giving me the opportunity to contribute to it. The work that I'm going to present, spike-based embeddings for multi-relational graph data. This is work that I've done at Siemens in Munich with my colleagues Jose, Victor, Marcel, and Thomas. Currently, I'm working at ESA in the Netherlands, actually. But I'm also continuing on this kind of work here at ESA. So first of all, why should we be interested in knowledge graphs or multi-relational graphs? And the nice thing about multi-relational graphs is that it can be used to model a lot of different systems and structures. For instance, molecules can be modeled as graphs, social networks, well known for anyone here, or like medical studies, like the relationship between diseases, treatments, chemicals, side effects, studies, and so on. And the question that I want to raise here in this talk, or that I raised in this work, is how can we process such data structures using spikes? That's also what I'm going to talk about in the next 15 minutes. Now, first, as a brief introduction, what are knowledge graphs or multi-relational graphs? They consist of two main building blocks. The first one being nodes, these bubbles representing entities and concepts, and edges between these nodes representing relations between entities and concepts. So as an example graph, here you have a graph of like a movie where we have an actor like Carrie Fisher. She can have a professional actor. She plays a character which appears in a movie. So you can already see it's quite flexible in how we can model different systems here with edges and with nodes. A different way to represent this is as a list of triples. So this is always subject, predicate, object, or like node, edge, node. Like always one of these links here, like Carrie Fisher has profession actor, and we can just summarize the whole graph with a list of these triple statements. So that's an alternative representation of a knowledge graph. So what can we now do with these data structures? One thing we can do is ask new questions, like based on the knowledge that we have accumulated here. We can ask questions like whether a link should exist or not. For instance, does Carrie Fisher appear in Star Wars? And the answer to this would be yes, of course, since she's playing a character who appears in the movie Star Wars. Another thing we can do is node classification, where we would look at like the structure of a node, like what is it connected to, how does it relate to other nodes, and then figure out whether it belongs to a certain class or not. For instance, is this a real person or a fictional person or not a person at all? Now, a big question is, how can we do that? How can we do these inference tests on graphs? A classical approach is to build, to do feature engineering, like to build rules from our graph to figure out new relationships between our data points. This is like engineering filters for image recognition, like edge detectors. But this is quite hard and doesn't really scale well to big knowledge graphs that are very complex, maybe even unclean, and have missing links and so on. So a very prominent model nowadays, or approach, is to find new representation for each entity in the graph. So instead of using the symbolic structure, we want to find a new representation of the graph in a low-dimensional vector space. So how this looks like is that for each node, we want to find a new node embedding, like for instance here, a two-dimensional vector in a vector space. So each node here, like these would be the node embeddings, and for each node in the graph, we'd have like a list here of two-dimensional vectors, each vector representing or being the new token that we use for this node. And we do the same for the relations, where each relation type is represented by a vector or something else, like a matrix again. And usually, like we couple this with a scoring function, theta. And this scoring function, we can give the node embeddings and relation embeddings for a triple, like for a subject, for a predicate, and for an object. and then calculate a scalar value which gives us a likelihood estimate or some metric whether the edge SPO, like this triple, should exist in the graph or not. So the two embeddings plus the theta function are our replacement for the knowledge graph. And then we have vector replacements here, like vector valued quantities that we can use downstream in machine learning approaches like support vector machines, random forests, deep neural networks again. And yeah. So of course, when we just randomly initialize everything, this doesn't work. This will have nothing to do with our original graph, but we can train these embeddings to become very good at capturing the information contained in our graph. We do this by using the edges that we have available, using them as a teaching signal, and then training these node and relation embeddings using gradient descent. And after training, we can then use the theta and the embeddings, for instance, to do the link prediction task simply by swapping here or entering here the embeddings are a subject predicate object that we want to evaluate. Like Carrie Fisher appears in Star Wars, we'll now get an evaluation based on the knowledge contained in the graph, which is now contained in the embeddings, whether this should be true or should not be true. Now, the question is, can we do something similar with spikes? And the answer to that is yes. So there is a way to do that. There are probably many ways to do that. The way we found is that instead of mapping nodes and relation types to continuous valid vectors, we want to map them into the spike domain, so to spike trains. And what we found how you can do this is that nodes can be represented as the first spikes of a population of neurons. So this would be one node here, represented by, for instance, 3 neurons. And every neuron can only spike once. And the time to the first spike, like this whole pattern here, encodes now like this layer organa node. So the temporal pattern now represents this element of the graph. We can also do this for other elements in the graph, and we'll get slightly different patterns depending on how these nodes are related to each other. And relations are then represented as spike time differences between these patterns. So we take the spike time difference between the first neurons of the populations, between the second neurons of the populations, between the third neurons of the populations, and so on. And then we compare this to the expected spike time differences that we like the ones that we expect to be true to see when this relation is true. So Lea Organa appears in Star Wars should be true, so these should match. Of course, when we compare it to another relation like has child, this doesn't make sense. So there should be a mismatch, a big mismatch actually. So how does this look in practice? We implemented this with a simple integrate and fire neuron model, which can be solved analytically for the spike times, or like for the time to first spike. But you can also use other models as long as you can calculate the gradients with respect to the spike times. Like for instance, last year there were a few models presented by Komsa and Girls et al. Here at this workshop, and this year there will also be a talk about gradient descent in spike-based system by Christian Pehle tomorrow. So we take this model here, and these are like our neurons in the neuron populations encoding the nodes. So this would be the representation of one node, the representation of another node. Now these bubbles are the neurons. Of course, we have to drive them with some input, otherwise they won't do anything. So we use fixed spike inputs, so also a population of neurons where each neuron spikes once, and weights which can be trained. So by training these weights here, we can change the output spike times. And these spike times here now, like these patterns, represent the node embeddings. This is what we then use. We take the time differences, then we can decode the patterns and see whether, compared to the relations, and see whether a relation should be true between these two populations here or not. This is exactly this theta function, but now we have the spike times here, and again, the relation embedding. For training, we just use a loss function that depends exactly on these scores, so on the spike times, and the training graph, of course, and then we can optimize the spike times or like the spike embeddings and the spike time difference patterns using gradient descent. What we get then is something like this. So here in this graph, we have on the x-axis the time. On the y-axis are different neurons. The black, so it's a spike raster plot. The black dots here are the fixed input spikes. And between these gray dashed lines are the spike times of each, like of different populations encoding different nodes. And we also get the relation embeddings, like the expected spike time differences. Here you can see that we get a variety of temporal patterns emerging that encode different different relationships between concepts in our graph. So this can be very, very complex, like here on the bottom, but also something very similar and familiar to all of us, like coincidence detection, that two patterns, or like two concepts are very close to each other when the spike time patterns are very close to each other. You can also see that here we get actually negative spike time differences and positive ones. So the spike time ordering is also important, but this depends on how you choose this distance function here. So if you choose this to be symmetric, then you'll also get embeddings that only depend on the pure absolute spike time difference. So as a small example, here we use this on a graph encoding the relationships between countries and geographical regions. For instance, Italy is located in Europe, would be a triple. Slovakia is the neighbor of the Ukraine. Slovakia is also the neighbor of Hungary, and so on. And we can train our spiking neurons on this data set to get the spike time embeddings. And afterwards, we can evaluate like new facts. So for instance, what are the neighbors of Romania? So we would ask, like, this would be subject, this Romania, the predicate would be neighbor, and then we would test out all possible predicates, like all other countries and region, and see how our spike time embeddings rank these, like how good the patterns actually match. And we can use the scored and this theta function to make a list of sorted sorted candidates, where on the top we have the most likely neighbors and on the bottom we have the least likely neighbors. So when we do this, like here are the first 5 neighbors. You can see here on the map, these are of course the closest neighbors to Romania. When we go further, we get neighbors that are a bit further away. So this is exactly as we wanted, and the spike times, or like our spike patterns, encode this information. Now there's one small detail, of course. When we do this, our graph has to be static. So when we have a new node that wasn't present on our graph during training, we don't have an embedding for it, so we cannot do inference with it. There's a question, is there some way to deal with this scenario? So what about nodes that are not seen during the training? And there's a very famous and nowadays often used model that has many nice properties. This is only one of the nice properties, called graph neural networks, that can deal with exactly this kind of challenge. So here the idea is that we don't just take the node embeddings as they are, but we squeeze them through like a neural layer, where we enrich the embeddings and update them to get better embeddings, which we then use for our scoring. So this is the graph neural network part, where we update each and an embedding, like for instance, the embedding of this red node, by looking at its neighbors, the blue nodes. We collect the embeddings from the blue nodes, average them, and use that as the new embedding for the red node. And we do this for each node in the graph. So we apply this like a filter mask over the whole graph. That's why it's also called graph convolutional network. And this way we get an updated and enriched embedding for each node in our graph. The nice thing is here that we basically collect neighborhood information. So our embeddings now know something about its direct neighbors. And if we repeat this process, we would collect information about neighbors that are further and further away in the graph. Now, when we have a new node, it will most likely be connected to other nodes in our graph. So we can just take the neighbors, take their embeddings, and calculate an embedding for our node, and then use this node embedding in our like further inference pipeline. So we did exactly this we tried this out for a spike-based coding scheme. So we have this here as a proof of concept.
Dominik, 1 minute to
I'm
go.
almost finished. So here, this is exactly the same architecture as before. We have the fixed spike inputs. We have the initial spike embeddings now. And then we have this kind of like routing neighborhood aggregation layer. And this feeds again into another population or like populations of spiking neurons. Here they follow approximately this dynamics here where we have a synaptic kernel. We are averaging over the neighbors n. So these are like these initial spike embeddings. And we do this separately for every relation. So we kind of have a filter mask for every relation that we can train as well. So we did this for smaller data sets, since it's a bit hard to simulate this efficiently. So the simulations were quite small, so we did this on handcrafted smaller data sets, but you can already see that the performance here is quite competitive to more like standard graph embedding models, and it does learn appropriately. And the very nice thing here is that to reference the motto of this workshop, that the spikes flow. So the whole calculation is completely asynchronous. So usually in graph embedding, you would first update all like embeddings once to get the orange one. And if you continue this, like you have layer-wise locking. But here you can see that some of the final spikes already spike, neurons already spike, even before we have presented the whole initial embeddings. So everything is happening at the same time. And this also means that not all of these spike times here in the initial layer are needed to update or to get the final spike embeddings. So it's a pretty sparse computation, which I think is a very nice and cool feature here. So where do I see this going? I think this can be used to learn spike representations of various complex data structures, and we can combine this then with traditional spiking neural networks to do neurosymbolic reasoning with spikes, which I think is a very exciting topic and maybe future direction. Right now, I'm working on moving this from single spikes to spike trains. And if you have any questions or you have cool ideas how this could be combined here with your work or anything else, please feel free to reach out. And with it, I would like to thank you for your attention, and I'd also thank my colleagues for the awesome time at Siemens and also for the awesome time that I'll have at ESA. Thank you.
Thank you very much. I see again lots of questions, so the talk was very interesting. And I will only ask two because we need to move to the next speaker. So the first one would be, each vertex in a representative knowledge graph requires a population of neurons. How many neurons are required in each population for a given precision of predicates, relationship types, and does this rely on properties of the knowledge graph, for example, maximum degree?
Yes, so this really strongly depends on how large your knowledge graph is. So currently, each vertex, like in the data sets that I used, it was something between 12 to 32 to 64 neurons per population. For bigger data sets, like really the state of the art, like Freebase and WordNet, it's sufficient to have like 100 to 200 or even smaller. So it strongly depends on the structure of your knowledge graph, how big it is, how many entities you have. Yes. This, of course, one kind of, like in my opinion, one downside, since it's a bit wasteful to have like 100 neurons and each neuron only spikes once. That's exactly why I'm currently looking into replacing this by only having one neuron that spikes several times, which would be a much nicer coding approach for this.
Interesting, thanks. Then the last one from Thomas. With the spike-based representation, is it guaranteed that there are any embeddings that work? What is the relationship between the dimension of the embedding and the size of the graph?
Does that work? So I think the second part I also partly already answered. But the first part, so it will always, that's not simple to say. Like you do in principle the same as a machine learning, where you have like a train graph, you have your test graph, and you have a lot of ambiguity, since so there are like two approaches. You have the the closed world assumption and the open world the open world assumption. Closed world meaning that you only have a list of triples that are true, so you know that this is a fact. But there are a lot of triples you can create where you have no idea whether they are true or not. So you can say, okay, all of these triples are not true. This is basically not what we want, because then we would have a model that we cannot do inference with. So we assume that it's undecided for every other triple. And during training, we have to generate negative examples. So we kind of guess what is true and what is wrong. So you're not exactly guaranteed that it will capture everything correctly. But the most important things, like the things that you're really interested in, most often work quite well. So the embeddings capture the structure and it generalizes well enough. That's exactly the reason why people use this or started using these methods, because you can really compress information in a knowledge graph and use that. I hope that answered the question, because I wasn't entirely sure what the question was.
Okay, thanks again. So I think we need to move to the next speaker. So thanks for the presentation, and I guess we can chat with the participants during the other presentations. Thanks again.
Thank you very much, and thanks for the questions.